All right, so welcome everyone to this new lecture about COG, and this time it's going to be about tactics and how to automate things. And we will also talk a little bit about the challenges regarding handling names in languages, introducing a concept called locally nameless and a library for that. So very welcome, Elias.
Thank you very much. So let's get right into it. So as David said, this lecture is a two-parter. We will be talking about tactics in general and different ways of working with tactics and automation. And I will talk about an alternative standard library that exists that's called TLC. And this is, if you've done the chapter of book 2 of the Software Foundations that talks about tactics, it's called libtactics. That's from this external library called TLC. And from there, there's a quite natural segue into talking about a particular representation of name binding called locally nameless, because this library TLC has support for this. But as you say in French, I didn't take French, I took German, but I will give it a shot. You say, il y a plusieurs façons de plumer un canard. And that roughly translates to, there are many ways to pluck a duck. Here we have a very simple theorem. We say that for any property P, we have that P implies P. And once we've done our introduction, we introduce P, we introduce HP, which is the proof that P holds. Then there are many ways to solve this goal. We can do apply HP, we can do exact HP, we can do assumption, we can do trivial, we can do auto, we can do e-auto, we can do intuition, and I'm sure that this is not a complete list. There are many ways of doing things in COC. I think I mentioned this in the first lecture, that sometimes it feels like there are a bit too many ways to do things. But I'll try to give some kind of structure about what kind of tactics there are, how to think about them, how to work with them. So as you know by now, in general, it's the case that you have some goal, meaning you have a collection of hypotheses and you have a conclusion that you're trying to prove. And you apply a tactic, and one of two things can happen. It can produce 0 or more sub-goals, or it can fail. Hopefully it produces 0 more, hopefully it produces 0 sub-goals. That means that it solved the goal that we were currently looking at, but it might produce sub-goals. It could also fail, and there are sort of different kinds of tactics. You have these tactics that never fail. For example, you can always write simple. Nothing might happen. It might try to simplify, but fail. If you write auto, that also does nothing. It will try to solve something, but if it doesn't, then it's like you did nothing. There is also a special tactic called ID-tac, which is the identity tactic, which always succeeds and does nothing. That can be useful when writing tactics of your own sometimes, or when you just want to try stuff out and you need a tactic for syntactic reasons. There are some tactics that fail if the tactic doesn't solve the goals, if it produces more than 0 sub-goals. So for example, reflexivity is one. Congruence is one. Assumption is one. So that expects the tactic to solve the whole goal that we're currently at. There are some tactics that fail if it produces a sub-goal that is identical to the current sub. So if you try to do a rewrite and the rewrite succeeds because there is something that matches, but the goal that you generate is exactly the same as before. So if you have the identity equality in your hypotheses and you try to rewrite using that, then the tactic will fail even if it finds something to rewrite. And for completeness, of course, there's a tactic that always fails. There might be more than one actually, but I know of one that's called fail. And that can be useful when you're writing tactics of your own. We will see examples of that later. So these are sort of the kinds of tactics there are. In addition to these tactics, you have other ways of structuring your proof. And I'm sure that, I mean, you've seen all of these tactics, except possibly ID, tag, and fail. You will also have seen the things that I'm talking about next, but I'm sort of trying to give a complete picture to sort of give you a mental model of how things are. So as you know, you can just write your proof script as just a list of tactics. Here I have something that was from the very first lecture, that n plus 0 equals n for any n. And we introduce n, we do induction over n, and then we have two cases. We have the base case, where we do reflexivity, and we have the inductive case, where we have to do a little bit more before we can do reflexivity. And if you want to, you can focus the proof. And when you focus the proof, you write one of these bullets, for example, the minus here. And that means that we're now zooming in and looking only at this particular sub-goal. And when this goal is finished, then you need to use the same kind of bullet in order to do the next one. So this thing forces you to sort of have sibling sub-goals on the same level. It has no meaning in a proof, like it doesn't help the proof in any way, it doesn't make a difference for the prover. It just helps you as a prover, you, the human prover. So, and you know that there are many different kinds of bullets. You may not know that there is a prescribed order for them. So you want to go by number of dashes needed to produce the symbol. So the first bullet should always be minus, the second bullet should always be plus, the third bullet should always be a star. The reason I know this is that if you do them in a different order and then try to auto indent, then things get messed up because it's expecting a minus to be less indented than a plus. So the whole point of focusing is to help you structure your proof so that you know what's going on. And also, if things changes, then you know which sub-goals didn't finish, because you know where a sub-goal is supposed to end. So there's basically no excuse for not focusing your proofs, as far as I'm aware. Some people write their proofs as the example on the left, even like professional academics do this, but I've never seen I don't have a good motivation for why you should do this. However, there are different ways of focusing. So you've seen the bullets. You can also focus on a single goal by using braces. So here, for example, we've done it's the same proof. We do induction, and then we do a brace saying, and that basically says focus on the current goal, and then when that's finished, I'm going to write another brace to show that I'm done with this goal, and then you can continue with the rest. And this is slightly different. It's different because it doesn't care about sibling sub-goals. It's also different because it allows you to focus on a different goal, which can be useful sometimes. In this case, I've done something not very useful, is that I've done induction, and then I've said, I want to prove the inductive case first. So I'm going to write 2 colon and then a brace. And that now means focus on the second sub-goal, and then let me finish that, and then I will do the base case. So as I said, this particular thing is not very useful, but sometimes, for example, maybe you do a replace, or you do a tactic where you apply a tactic or a lemma that gives you a simple sub-goal that you'd like to get out of the way first. So this can be a way of sort of skipping the current focused goal and, as a parenthesis, do this thing. So the way I personally use this is So personally, I use bullets whenever I have more than one goal. I remember we will actually see some cases where it might make sense to wait with adding bullets. I'll show you that later. And then I use braces when I'm sort of sidestepping the main story of the proof. Here we have some theorem, it doesn't matter what it is. We're in a particular case, and I've done an assert. I want to assert that there is an n such that if we do a lookup in the environment, then we get that n. And the way I think about this is that I'm telling a story with a proof, and I want to say, so here we know that x has some value on n, and then in parentheses, which we can show by doing case analysis on this thing, and here are the cases. You can see we can have bullets inside of braces, and then we're done. And then we jump out of the parentheses, and we keep talking, basically. So this example comes from the running example of this first part of the lecture. So I'm just going to go through that briefly so that we have, so that we know what we're talking about. So the example that I've come up with is a very simple SSA language, static single assignment, where you have these registers, and the registers are assigned to expressions, and the expressions could look like 1 + 2. They can also mention previous registers. You can do R0 times 3. You can check if a value is, or if an expression has the value 0, and if it does, you do this thing. If it doesn't, then you do the other thing. And then in the end, you have some final expression. So expressions are numbers, registers, addition, multiplication, or this is 0 conditional. And then programs are basically lists of expressions where the register number is implicit. So the first expression is going to be bound to the variable R0, the second is going to be R1, and so on and so forth. During execution, we have some environment that maps natural numbers, that is the index of the register, to natural numbers, which are just the results of these expressions. And we have, we can evaluate an expression by giving it an environment, sort of the previously bound registers, an expression, and that's going to give a natural number. And you'll notice here that I've written this as a partial function. So the result, we could fail if the expression uses a register that's not been defined yet. And then there's a top level function that evaluates an entire program, sort of chaining the environment as we go along. And the thing that we're trying to prove, we can define well-formedness, saying that a program is well-formed if it only mentions assigned variables. So it doesn't try to do anything with it doesn't mention R1 here, for example, before R1 has been defined, or R2 or R3. And the main theorem that we're going to want to prove is that if we have a well-formed program, then that program evaluates to something. Okay? So let's have a look at what this looks like in Coq. I'm going to define variables to just be natural numbers, but I'm defining it as a name so that I can distinguish between the two. We have expressions, which are natural numbers or variables or addition, multiplication, or this if condition. We have programs, which are basically just glorified linked lists. We have this well-formed expression. An expression is well-formed given some max variable if basically the only interesting case is this one, where we're saying if the variable is less than this maximum defined variable, then the variable is well-formed. Everything else is just sort of chaining this rule through. And then for a well-formed program, we have this auxiliary relation, well-formed program prime, that takes some maximum thing. So we're going to start with this maximum thing being 0 and say, okay, so the first one, the first expression should be well formed with the maximum variable 0, meaning no expressions allowed. And then the next one, we increase it by 1 so that we can take the previous ones. Finally, we have our evaluation functions. We can define an environment. That's just a list of natural numbers, and then we're going to use the variables as indexes into this environment. And a natural number evaluates to itself. Note here, this is the partiality. The result of this is an option nat and not a nat. So a nat evaluates to itself, a variable evaluates to whatever the result of looking it up is, including none if it turns out that this thing, if this variable is out of bounds for the environment. And then the rest of them is just going to say evaluate the sub-expressions, check if they have result, and if they do, then do addition or multiplication, or this one is slightly more involved. It says if the condition is 0, if it has a result and it's 0, then do the then branch. If it's any other value, then do the else branch, and if it fails, then fail. Evaluating the program, we have this helper with the current environment, and that's going to be nil to begin with. And if we have an assignment of register, I've called that plet, then we evaluate that expression, and if that succeeds, then we evaluate the rest of the program with our environment now extended with the new value that we just assigned it to a register, basically. And in the end, we just have a result. If any expression fails, then the evaluation of the whole program fails. The exact details aren't super important, because what's interesting is that what we want to talk about is sort of the proofs about this. So I wrote this horrible proof script. I should have just put it all on one line just to make a point. But this is how some people write their proof scripts, where basically I've done some indentation to help myself, but it's very hard to see where one goal starts and one ends. So we're going to start by improving this. So we do induction, and then we see that we have 5 goals. Again, look here, we could do 3 colon then a brace, and we would focus on the third one if for some reason we wanted to do that first. But for now, we're just going to start by adding bullets. So here's 1. And now, because we've started a bullet, we have to keep going with the same one. If I try to do a plus, it says, no, wrong bullet. I was expecting a minus. So we do that thing. And then, yeah, let's just trust that, subs here. Let's just trust that the proof here is correct. Here I have an assertion, so I'm going to do my trick where I want to prove this assertion, but I don't really want to add another bullet, because if I add a bullet in order to prove this thing, then I have to continue with another bullet, even though logically the rest of this proof sort of belongs on this level. So instead, I'm going to write this as a proof like this. Here we're going to do bullets again. I'm going to do bullets again. Note here, I don't care at all about what the proof script is doing, except how it's generating new goals. So it's on purpose that I'm not talking about what's actually going on in these proof scripts, because as long as they pass, we don't have to care. Right, here we're done. We have to focus. So let's just process the proof script until it tells us that we're done, and then we'll add a bullet at that point. Right. Oops. And here we have 2 subcases. And like that. Great. And then, yeah, let's do the same thing here. Start with a bullet here. And then there's another assertion. So let's do the assertion trick of adding a brace here. And then we just continue, and let's see if there's, yep, here's the second case. Yes, good. So this is going to be a lot nicer to work with, because now we know sort of where one case of the proof starts and where one ends. So I'm going to keep improving this proof script as we go along. So this is now just making it ripe for improvement, basically. So let's keep moving here. Someone was funny on the internet once and said that there are two hard problems in computer science: cache invalidation, naming things, and off by one errors. And naming things in the context of Coq is annoying. It takes time. You need to come up with names that are supposedly good. So it's very easy to be lazy and just say, well, there will be names generated, so I'm just going to use those. That's fine. I can look up what they are. But I'm going to implore you to not do this, to avoid this as much as possible. Because, for example, if you have some proof and then you've done something, you've just trusted the automatic numbering of hypotheses, then you have some H0, H1, so on. And then you change some definition so that maybe there's now an additional hypothesis in scope. That means that your entire proof script is going to be off by one, because all of a sudden there's another thing that gets the name H1 and H0, and what used to be H1 is now H0, is now H1, and so on. So this if you have something that you're going to live with for a while, that makes your life a lot more difficult, because every time you make a change, you have to sort of go through and manually update things, which is very annoying. I have also learned the hard way that sometimes you update the version of Coq, and that actually changes the automatic numbering scheme of things. So if you're trusting the automatic numbering, then things can break even when you haven't changed anything. You've just updated the proof. Sorry, you've updated the version of Coq. So let's have a look at how one can name things then. Most tactics in the standard library that introduce new terms, they support naming somehow. You've seen this in the book. You've seen destruct n as, and then you can give, in this particular case, you have two different branches. One, this is the zero case. There's no variable to name, and here we've given the other thing n prime. I'm assuming this is a natural number now. When you do induction, you can do induction L as, and then you can give these things names. A lot of the time, Coq will be clever with, like if you do induction L, it's going to call the list L as well. So in here, it's going to be called, this will be called N if you don't write anything else. So a lot of the time, it's like if it's just one thing, then it probably gets a name that makes sense. But you can give names to things. Assertions we've seen, you can just say assert and then something you want to assert, but you can also give it a name so that you can use it later. Another thing that you may or may not know about is that the way you declare your data types actually matters as well. So here I've written my expression, just a natural number and the variable addition. And if I now do destruct on one of these things, it's going to give then this thing is going to be n. The variable is going to be called v, and these expressions are going to be given their names e and e0. So it takes the first letter of the corresponding type of what's inside them. Whereas if you write your inductives like this, where you actually give it a name like this might look like I know dependent types now, but I'm not using this variable anywhere, so why should I give it a name? Well, one point of giving it a name is that when you do destruct, it's going to call this n, it's going to call this x now rather than v, and it's going to call these e1 and e2, assuming that these names are available. Otherwise, it's going to give other numbers. So this can help you in doing these things. Note that it is possible. Let me just jump back to Coq real quickly. It is possible to say, let's do the addition case. It's possible to say, see if I can make this work. E1, E2 are expressions, and let's call this WF1, and this one WF2, and then the result of the whole thing is that. You can write it like this, so that when you're doing induction, for example, let's see if we can find a place where we're doing induction over this thing. Let's jump to the, now it's easy to find the addition case, by the way, because we have bullets. It's calling it age. Did they do something? It's strange. I really thought that it would, when I tried this before, I think that it gave these actual names. Let me just see if I can make this work. Nope. Okay. Sorry about that. This is the demo daemon where this worked before I tried this. It worked before when I tried this, but it isn't working now. Sorry about that. So forget what I just said. But this is, at least it's good for when you're defining your data types. I'll see if I can figure out what went wrong with the other thing and get back to you on Slack. But okay, but we just said that naming things is annoying. So how can you avoid naming things? So here's an example that you might have come across, where you do destruct on something. Here I'm doing destruct on some induction hypotheses, and I get some n, and I get some HEQ, and then I do rewrite HEQ. And immediately after this line, I don't care about HEQ. It's just going to be there. It's going to take up namespace. It's going to take up space in my goal view. So it's just going to be annoying. So you can write clear HEQ when you're done, but there is a neat way where you do destruct, and then you write an arrow in your introduction pattern. So whenever you have an introduction pattern and you introduce an equality, you can do either a left arrow or a right arrow, and that's going to be the same thing as after this, do rewrite to the direction that you've given, and then you clear the thing. And then when you have enough automation, you can try to write your proof so that you find your hypotheses automatically, rather than giving them names, and then you don't have to give them names anymore, because your proof isn't going to rely on it. There is a heavier alternative that I'll talk about later, where you match on the goal, but we'll get to that later. First, there was a question: was it induction on well-formed or the AST itself? I'm pretty sure it was induction on the AST itself. Yes. Oh, sorry, on the well-formedness. So this is well-formed expression, and that's what I updated, and that's why I thought that giving this a different name would do that. Yeah, I agree that it's weird, and I'm pretty sure that I tried it before and that it actually did work, but let's not troubleshoot now. But what we will do is that we will name some things. I typically don't. I could write induction HWF here as, and then give a bunch of cases. But in general, I think there are just too many cases for this to be reasonable. And most of the time, the names you get make some kind of sense. Like, it's fine as long as the names are the same at the beginning of the bullet. Then I think it's fine. So we'll see where we can. We've already done a good job of. Oh, I've removed the induction. we've already done a good job of naming this assertion here. And here we're destructing this thing. It happens to get the right name n, but we can destruct this as n, and then all right, of course, this is which case is first. This is the sum case first, n, and the none case. So this, in this particular case, we're not changing anything, but at least we know that if for some reason the destruct, maybe we change the proof later so that there is an n in scope, then at least we know that we will get told that you can't name this n, rather than be confused about this n now referring to a different n. Now we're doing destruct hex, that's this one. So let's do the same thing here, but now we have an exist, so that's going to be n, and then some equality like this, and now we can say exist n, and apply heq. So that's already a lot nicer now, that it's not h0 and x, which means different things when looking at, because x is usually variables. So now we get something that's nicer. We can do the same thing here. We're going to destruct this thing, this induction hypothesis, as n1 heq. We're going to destruct this as n2 heq, heq2. And now what we did was we did rewriting, and we did rewriting with these things. So rather, we could rewrite heq, we could write heq2. But instead, what we're going to do is we're going to replace these things and not introduce them as names at all, and just say, we're generating an equality, so find that equality in the conclusion and do that rewrite. Note that if you need to do the rewrite in another hypothesis, then you can't use this. This is just for the goal. It's not doing the rewrite in the entire thing. Now we can say n1 and n2, and we're back to reflexivity. So this is a lot nicer, I would argue, at least. So this happens to be more or less exactly the same proof, just that we have a star there, and this is going to be, see if we can be clever with multiple cursors, and like this. You can remove these rewrites. Now we're matching on something. We're going to match on n1, and in this case, it's n2. In this case, oh, sorry, n3. So these are small things, but hopefully you agree with me that the proof that we've written, like, it was a little bit of extra work, but it's a lot more. It's a lot easier to follow, because you know exactly where a name was introduced. That's visible in the proof script, and also you have the. It's more robust to change right now. Let's see if yeah, to save time, I'm not going to do the same thing here. I think you get the point already. So let's go back to the lecture. There's a special kind of tactic, which is called tacticals. And a tactical are tactics that take other tactics as arguments. So for example, you might have seen the semicolon that says run tactic 1, and then on all of the subgoals that were generated by running tactic 1, you run tactic 2. You have the or tactical that says try to run tactic 1, and if that fails, run tactic 2. You can try a tactic, and that says that run this thing, and if it fails, then just do nothing. So that allows you to take something that might fail and then just ignore if it fails. You can repeat a tactic. That means run it 0 or more times until it fails or until it generates an identical subgoal as the one you have. You can repeat a tactic a certain number of times. You can require that a tactic actually produces a new subgoal. So you can say, oh, let's say that you have a branch of semicolons, but you know that it only makes sense to follow that if a certain tactic succeeds, and actually makes a difference. For example, if you can actually simple something, or if you can actually unfold something. So then you can use progress to say, do this thing, but if nothing happens, then fail immediately, so we don't continue. You have the solve tactical that says run tactic and fail if it generates more than 0 sub-goals, meaning if it doesn't solve the thing, then that's a failure. So I'm expecting this tactic to solve the goal right now. You can also say run this particular tactic on the nth goal. You can have, this is an index, it starts on 1. You can have ranges, you can have 1, 2, 5, and so on. And you can also do all colon. So for all cases, run this tactic. So this is the one case where it might make sense to wait with focusing, because once you focus, this thing won't work anymore. This is running the tactic on all goals that are currently in focus. So you're going to want to, if you know that, oh, I'm going to start the same way in all my goals, then you could start after your induction, you do all colon and then some tactics, and then you start focusing. Some of these tacticals, they will work with a list of tactics. Sorry, there was a question in chat. Is it a good idea to use numbered goals as in n colon tactic? Is it stable between coq versions? I'm pretty sure that it's stable between coq versions. It's not, however, stable if you extend your type. So let me give an example. When we are here, we know, for example, that in goal number 1, 2, oh, this is weirdly indented, sorry about that. We can do all colon simple to begin with. We might do in 1, 2, 3, 4, and 5. In 3 to 5, do destruct IHHWF1 as N1, like that. And that's going to, so that's basically doing this thing, but for all goals at the same time. I don't do this a lot, especially not with numbered goals, because as you say, you ask is it a good idea? The bad thing is that I might later decide to add a case here. Let's say I add something here, and in that particular case, it no longer makes sense to do this thing. Then this is going to break because these numbers are now off. That makes sense. So it's possible to do this, but I agree with you that it's not a good idea for goals for proof developments that will evolve. It is quite nice, however, when you are exploring a proof. So when before you know what the proof is going to be like, you can try sort of, okay, so can I do this for all? Can I do the destruct thing? Can I do that for all? Okay, no, okay, so that doesn't exist for all of them. So it's a way to sort of explore multiple branches at once, if you will. But that's mostly how I use it, for exploration rather than writing proof scripts. But I can see cases where all would be useful. Thanks for the question. So I was saying that there are some tacticals that work with lists of tactics. So for example, the semicolon tactical can take a list saying on the first sub-goal, run tac 1, on the second sub-goal, do this one, and so on. So it allows you to sort of branch on if you know which sub-goals are going to be generated. Again, this is not going to be stable if you change the way the sub-goals are generated by the tactic, but it's useful sometimes. You can give several things to solve. That says try to solve the thing with tac 1, and if that doesn't succeed, try to solve with the next one, and so on. So if you're in the case where you know that one of these will work, then you can give several ones. There's also a first tactical that only works with a list that says do run the first of these tactics that does not fail. So it tries them all until one of them fails. So two useful patterns that you can take with you is, for example, when you're doing an assertion and you know that the proof of this is going to be really simple. So then rather than focusing on using braces or bullets or something, you can do I do a semicolon and then I say apply foo semicolon auto. So that this is all I need in order to prove this assertion. I'm using the powerful foo lemma. And then for the second case, which is sort of continuing where I am, I'm going to do nothing. So this is a nice way to sort of get rid of very simple subgoals without sort of breaking the flow of the proof script. There's also this thing which is very useful where you combine two tacticals where you say, here we're doing induction E, and then we say try solve. That means use the solve tactic, basically try assumption. If that doesn't work, try apply foo and auto, and that doesn't work, some other tactic. But rather than failing if none of these work, we allow this to fail for some cases. So this way we can, if we know that, oh, we're going to solve a bunch of goals by just doing these simple things, let's just be lazy and apply them to all sub goals, and then because we did the try, we're going to leave all other goals unchanged. So that's another thing. If we did semicolon and then said apply foo semicolon auto, apply foo might change the proof script in a way that you may not want to. Maybe you're only interested in doing this if this actually leads to solving the goal. So then you put it in a try solve. Right, so let's have one of these short breaks for questions. If anyone has anything that they would like to ask. Otherwise, this is a long and awkward silence that you can edit out. Is it possible to name a goal? Not in general, no, not that I'm aware of. It is, however, there used to be in the Software Foundations book, I believe, but they removed it. A thing called basically a small library called case, where you could say something like with cases induction WF, and then you said case. This you would for any, like, together with this thing, you would have said that, oh, the first case is going to be the NAT case, the second case is going to be the var case, the third case is going to be the add case. And then what this thing did, I'm misremembering the syntax, is that it would add a thing here. It would add basically a string value to your context, and then you would say case NAT. And this tactic would only succeed if this was the case that was actually generated there. So that was a way to basically, sometimes you will sort of write case NAT to know which case this is. This would be a way to formalize that so that it would actually fail if it was another case. So I think that was quite nice because it meant that you could sort of structure your proofs even more. Like it was the closest you could get to naming a proof. But I can also see why, like, it adds even more overhead to the actual proof, and it requires you to actually write these auxiliary definitions for the well-formedness thing, so that it actually numbers, sort of gives names in the right order. So I can see why they removed it from the Software Foundations book. But I think that thing is still around somewhere. But that's the closest thing that I've seen of naming a goal. It's a good question. If there are no other questions, then I will move on to talk about. Oh, there is a. Let's see. There is a by keyword for at least the assert and replace tactics for discharging the sub goal that I think is nice, but I don't think that it's a general construct. Yes, that's very true. So I was saying that you can say assert, and then if it's a simple thing, then you can say my proof, and then like that. You can say, oh, did I break something again? I keep removing the induction. All right, I did it with cases thing. Sorry, let me just unbreak my code. Lesser known Tory Braxton song. So assert blah blah, and then you can say by, and then, for example, like that. And now it says proofs is not complete because auto can't solve this thing. But if there is a simple way to solve it, so you can do. It works for assert. You said that it works for. Replace as well. So you can say, if you're replacing something by another, you can say replace blah by blah. So replace blah with blah by, and then the tactic that proves this thing. But it's true. This is just sort of hard coded for assert. You can't always do by. And then someone asked, does this case library preserve a proof if one adds another constructor? And there's an answer to that. It will make the proof fail when it gets to a case that's not what it expects, which is nice because it's a very clear error. Exactly, I totally agree. That's what's nice about it, is that rather than being halfway through a proof before you realize that, oh, I'm actually working on a different case, you get a sort of fail quickly effect. Okay, so I will move on to talk about automation. So automation, we've talked a little bit about automation. You've probably seen a little bit of automation in the Software Foundations book. So what automation does, it's actually quite simple in its sort of basic form. All it does is that it applies hypotheses that you have in your goal recursively. So it checks, is the current, this shouldn't say goal, this should probably say conclusion. So is the current conclusion already in our list of hypotheses? If it is, then we can apply that hypothesis and we're done. If that's not the case, then you can check, is the current conclusion the conclusion of a hypothesis? So basically, is there a hypothesis that is an implication where the result is going to give us that? If so, we apply it, and then we keep going recursively, because if it's an implication, that means that you have other things that you're going to have to prove, and then you can try the same thing by that. So when you add stuff to your hint database, for example, here you do hint resolve my pretty lemma and add it to some hint database, all that does is that it adds this lemma to the list of hypotheses that it's going to test when it's doing this thing recursively. So it does a few more things. It unfolds stuff. If you tell it to, you can say, oh, by the way, I want you to unfold this fixed point that I have. It doesn't unfold everything automatically, which is good, because sometimes you want a level of abstraction in order to make it find the lemmas and so on. It will do intros sometimes. It will also do simple sometimes to sort of, when it sees that it's possible, to try to be able to apply these hypotheses. So the idea of like the basic procedure of proof search is quite simple, and I think this thinking of hint resolve not as, oh, by the way, I want you to know about this lemma. All it does, it's basically the same thing as if you put that above the line in your goal. So tactics that you've seen. There are more of them, but some that you've seen is auto. That does, and you can say auto with some hint database if you want to. That's going to do proof search like this, and it's going to use simple apply. So simple apply, it's like apply, but it's a little bit cheaper to do because it's not as good at instantiating certain quantified variables. If you do e-auto, it's going to do proof search with simple e-apply, where e-apply means that you might have a quantified variable that you don't know exactly what it is, but we can introduce that as one of these existential variables and solve it later. So e-auto is going to be slightly more expensive, but it's also going to solve some new goals. There's also one that's good to know about called intuition, which is sort of specialized for doing logic reasoning. So if you just write intuition, that's the same thing I think as writing intuition auto. So intuition, and then the tactic that says do your thing, do your regular thing, but when you don't know what to do, you can apply the tactic that you provide in order to make progress. And what's good about intuition is that it will destruct branching hypotheses. So for example, if you want to show that P or Q implies Q or P, auto is not going to solve that because Q or P is not going to match anything that we have in the hypothesis. Whereas intuition, that's a proof procedure that knows that, oh, it's probably a good idea, but this is an OR, so I'm going to do a case analysis on that and see if we can solve this thing. So intuition is nice for that reason. It's also not very nice because it's actually going to update the goal. Auto is one of these tactics that if it doesn't succeed in solving the thing, it's going to do nothing. It's a no-op. Whereas intuition is it's going to try to solve it, and if it can't succeed, it's just going to drop you into the part of the proof script where it failed, or part of the proof search where it failed. So you will be deep in some sort of branching and you have no idea how you got there. So a good idea might be to actually try solve intuition, just to ensure that intuition only doesn't leave you somewhere where you don't want to be. So let's add some automation to this thing, because there are some things that are going to be simple. Let's start by just doing a semicolon auto. See if that helps. That didn't help at all. Let's do semicolon e-auto. That also didn't help. Okay. So then we'll keep going. Let's do simple here. Let's see, can we do auto here? No, can we do e-auto here? We could. Okay, so then we're going to try to, after our induction, we're going to do simple followed by e-auto. Let's do that for all the goals. And now we can actually get rid of the first of these. That's nice. We don't need to do simple. Did not auto do simple? That's a very good point. Apparently it did not here. I wonder if this is let's see where we're at. I wonder if this is because we haven't told auto to unfold this thing. Let's try to say hint unfold eval expert. And now I'm doing the bad thing of adding it to the global database. I'm not supposed to do that, but let's just try this now. No, still didn't work. Not sure why it didn't. Maybe because it's under a quantifier. It could be because of that, and that simple does. I'm not sure about that. That's a very good catch. Sort of contradicting what I said before. But for now, we're going to do simple and auto. Let's see if these look pretty simple. Let's just do auto here as well. At least it got rid of one of them, and which is the one that it didn't find. It's this one where we have none is not equal to none. I think maybe congruence can solve that. Yes, there's a little bit more automation. We're going to do a destruct here, and then from here it should be pretty simple. Maybe we can do e-auto there. Yes. We'll do destruct and then destruct. And I guess technically we don't need a semicolon there. Let's be clear about that. We'll do destruct, e-auto. Nice. Destruct, e-auto. Works. Nice. We have 3 destructs, and then we have another destruct, and for each of those it looks pretty simple. So let's do e-auto. And we can get rid of that. So now we're again to save time. I'm not going to bother with this thing, the rest of the proof. Let's just look at this one. So this is now a lot nicer. A lot of the things that were sort of a lot of the tiny details you can just e-auto is the closest thing you can get to saying, and then obviously what you want holds. So this is pretty nice. Let's move on to see if we can learn anything else that we can apply. So I was talking about matching on the goal. So tactics, there are kind of not really meta programming, but they sort of they support reflecting on the actual proof state, which you don't when you're writing your regular coq code, when you're writing the Galena code. So there's a tactic. I guess it's technically a tactical where you can say match goal with, and then you write the hypothesis here, and then you write your ASCII version turnstile, and then you write your conclusion, and then you write the fat arrow, and then basically if the goal looks like this, then apply this tactic. So for example, we can say match goal with, and then if there's a hypothesis, let's call it H, and its type is well-formed expert, and then I don't care about what well-formed expert is. I don't care about what the conclusion is right now. Here's the turnstile. But if this exists, I'm going to do apply WF expert eval. So that's a lemma that I had in H as, and then this thing. So basically, rather than me saying, oh, what's the name of this? I'm going to apply this thing. I'm going to ask Coq to say, if there is something that matches this thing, then do apply this tactic or run this tactic. There's also a very useful version of this where you can say use context to say if somewhere in the term that's here there is this expression. So if there is a match somewhere in the conclusion, then do a destruct on E. Let's see if we can do something like this in here. As you can see, these 3 cases are very similar. So I'm going to start by writing it in one of the cases. So I'm going to say match goal with, and then if there is a hypothesis that's an existential that does eval. Basically, I don't really care if there's an exists that has an equality. I don't care what the goal is. Then do destruct on this hypothesis as n, and then do apply the rewrite like this. End expected after. Oh, sorry, yes. So now you can see that it actually finds one of them. It happens to find number 2 before it finds number 1. That's fine. We can say repeat. They do these things several times. Still only finds one of them. See why that is? Let's copy paste this thing and do it again. And here's the annoying thing. It just says no matching clauses for match. We don't know if this is because there was no hypothesis that looked like this, or if it was because this tactic failed. This is unfortunate, but that's just the, let's see, IHHWF1. Yes, if we move this tactic out, we can see that, you've already used the name N. But I want to do this several times. So how can I do that? Well, I can use special tactics for generating names. So I'm going to say let N equals fresh N. So that says try to use the name N, and if it doesn't, try to use N1, N2, N3, and so on to generate a name that's close to N, and then store it in N. So now this N here is no longer a concrete name, but rather a generated name. So it picked N the first time. If I do this again, it now picks N0 for the second one. So this allows me to do repeat this thing. And then afterwards, let's just do e-auto. So now that worked for this particular case. So we can try to put this thing after our induction here. We can say try solve, and then this little thing. Let's see if that works. Can't be a period there. Right. So it's now it manages to solve all but 2 goals, which is a big improvement. So it solves this one, and then it's the final one here, because note that even if it does this thing, that's not enough. It's going to it also needs to destruct on this thing. But we could write that as a match goal with, and now I don't care about hypotheses. Annoyingly, you have to write this thing because if you don't write anything, that means there are no hypotheses, which is not what we want. So for any hypotheses, if in the conclusion there is somewhere we're doing match of something, call it N with, and then we don't care about what the result of matching is, then please destruct N. See here, right, and there as well. Note here there are question mark N, because that means sort of this is something, we don't know what it is. It might not be a single variable, it might be an expression, but introduce that as the name N. So do that destruction and then do e-auto. So now we could, if we wanted to, we could add that up here, but there's actually a nicer way that I will show you in just a second. There's another comment in the chat saying there's also a more lightweight way to tell Coq to do its normal naming thing on a particular thing for cases where you don't need to manually refer to it. Use question mark instead of a name. Exactly. Yeah. So this is because I was trying to name things. I could just say, I could just do this, and then it also works. And then because it solves everything, it doesn't matter if it introduces a bogus name here, because I'm not going to see it anyway, right? So this thing is useful to sort of solve common goals. It's even nicer when you're writing your own custom tactics. So here I've written a tactic. I've written LTAC destruct X colon equals, and then I generate names, and then I say if there is one of these things, then do the destruct just as before, and then we're going to try to rewrite in both directions, both in the left direction, and I'm going to rewrite both for the both in the conclusion and in all the hypotheses. And here's the or. If this tactic fails, then I'm going to try to rewrite in the other direction. And then if either of these succeeds, I'm going to remove it, I'm going to clear it. And if not, then because I have a try here, it's not going to do anything. So at least I'm going to still have the equality there. And then you can tell auto and the other automation tactics to use these tactics with some cost. So here I'm going to say with a cost of 1, the cost is typically the number of sub goals generated by something. With a cost of 1, you're allowed to use this tactic when you're doing automation. Here's a nicer version that uses where we have a manual one where we actually give it a hypothesis, and rather than matching on age, we do match type of age and say if the type of age is one of these exists with an equality, then we do the rewriting. If this doesn't match, then we use the fail tactic to give a good error message saying, oh, the age that you gave is not an existential equality. And then we have the auto version that actually tries to automatically find this thing. And if it doesn't find one of these things, then we fail with the error message, no existential equalities in context. So I could go back and actually write this so you can see it in action. But I'm running a little bit short on time, so I'm going to move on quickly because there is a nicer way. So the Coq standard library is okay, but there are nicer alternatives out there. And one of them is you've seen already if you've done the libtactics chapter of Software Foundation, if you've gotten that far. And that's actually from an alternative standard library, an external library called TLC. Here is the 90s pop group TLC, or R&B group TLC. They didn't invent it. A guy called Arthur Chargereau, here's him, is the one who invented it. And it has a bunch of nice things. So it has custom tactics that removes a lot of the boilerplate. I will show you examples in a second. There's an alternative standard library that has a bunch of things for lists and sets and maps. It also uses type classes a lot, meaning that you get nice notations that work for several different things. So you can use union for sets, but you can also use union for maps. You can use you can use the same notations. You get prettier proof scripts without clashing between different things. You should know, however, that this thing is no longer constructive. It assumes classical logic. This is typically assumed to be fair game, but you should know that this is the case. One of my favorite things that I think they should bring into mainline Coq as is the new introduction tactic called intro V, where it basically usually if you have something like this, then you always start your proofs by doing intros and all the same things that I wrote here. The only things that's interesting is which names do I give to the hypotheses. And this is exactly what intro V does. It jumps past all the quantified variables and instead it just lets you give names to these things. So that on its own is enough to use the TLC library, in my opinion. So some syntactic conventions regarding the tactics. Most of the new tactics, they will end with an S to distinguish them from the originals. So you have simples, which is like simple, but it's slightly better at unfolding. You have subs, which is like subst, but it handles circular equalities. You have inverts, which is like inversion, but it also does subst and clear afterwards, so you sort of get rid of it. There's applies, that's like apply, but it's better at handling quantifiers and so on. And the way to run automation is that most tactics, not all of them, because you have to add it by case basis. You have these two versions where you say tactic tilde or tactic star. And tactic tilde more or less means use auto on all the sub goals. Tactic star means use e auto on all the sub goals. Actually, it's slightly more involved. There's a different thing. I think I'll have an example later. But it allows you to write things like this. you write induction tilde n. That means induction, do the simple auto on all the subgoals, and for the rest thing, I'll just go simples and then rewrite tilde ihn. So I think this is a very lightweight way of getting rid of all the sort of semicolon auto, semicolon e auto, semicolon. So this is a very nice way of writing these things. It has nicer introduction patterns. I think I'll skip this for time. You can look at the slides if you want to. You also have very nice forward reasoning. So the sort of standard library in Coq has some of this, but this lets you do things in a nicer way. So you have let's h colon that says instantiate this lemma and call it h. So sometimes you want to do some kind of reasoning based on some lemma. The sort of standard way of doing that is doing apply my lemma in and then some hypotheses. But then you get rid of that hypothesis, and your new name for this thing is now what the name of the old thing that you applied the lemma in. So you can do this way. You can sort of introduce something new into your context, which is very nice. You can do forwards, which is like let's, but it also introduces existentials, meaning that when you combine it with automation, you can do you can sort of find what these existentials are. So for example, here is a well-formed program eval, and all I do is I do inductions HWF, semicolon, then do simples and star, and that apparently solved something. And then I do forwards and some deconstruction, and this is the lemma that I'm instantiating. So I thought that I'd show you before we take a short break how this might work in practice. So here I'm using the TLC library. I've actually changed this a little bit just to show some of the things that exist. Variables are now actually variables, and these are variables from the environment library of TLC. And what does that give us? That gives us, for example, the type vars, which is just a set of variables. So we can say that so the well-formedness expression is now parameterized over this set of variables. So we say that a variable is well-formed if x in vars. So if the variable x is in this set, then that works. A program, we can now say, as I've now rewritten this so that you actually define, sorry, I should show that here. You actually define a name of your registers. You can name it whatever you want. And the well-formedness says that you may not have used it before, and then you check the rest of the program with the singleton set x union vars. So you have these nice notations for handling sets and so on. But what's really nice about this is that so here's the thing I talked about. When you write, for example, simples tilde, this actually is going to write simples, and then it's going to run this tactic called auto tilde. This is something that's defined, but you can redefine tactics when you write double colon equals like this. So this lets me say that, for example, I only want you to use the things that I've added to this hint database, and the same thing for auto star. So this is going to run this tactic whenever I write a star. So the reason I do this is because I wanted to only use the hint database in case I want to add something like that. So let's see what this proof might look like. I will start by doing intro v hwf. Note that it introduces. Sorry, is it bigger? Note that it introduces e and env, just as they were named before. And then we can do induction hwf. That gives us the goals. Let's do induction tilde. Goals induction star, maybe. Okay. So let's do induction and then simples and then star. That solved one of them. The first one, what's nice about this thing is that sort of you have standard library for these things. Of course, you have to know what they are, but I'm going to want to use something called get sum. If you can do, is it apply get sum? Yes, and this thing is now in there. So rather than writing apply age or writing auto or something, I'm just going to say apply tilde get sum, and that solves that thing. So I could actually, so the rest of them, we know that now that basically all we want to do is destruct this thing. So let's write this little, oh, we can actually, I think we can do one better. I'm going to write a little helper tactic. I'm going to say LTAC, I'm going to call it cases match. I'm going to match on a goal, and it's going to say, if there is, oh, I think maybe we can just steal it from here because I'm doing exactly the same thing as I did up here. If there, no, this is not what I, where did I add it here? Yes, here we go. This says, if the conclusion of the goal has a match somewhere, then destruct that thing. Okay. So I'm going to, I think this is going to work. Now I can write cases match, and then I can, this now finds that I'm doing a match over this and does a destruct on that. Let's do cases match again. And then from here, I think I can solve it with eauto, yes. But now we have these things here where we have, oh, actually none equals sum, so we'll have to destruct this and do inversion and so on. So I'm going to add the, I'm going to say tactic notation cases match star, meaning cases match followed by auto star. Yes. And the same thing for tilde. So I'm going to sort of make this look the same way as the rest of the TLC library looks. So now I can write cases match star, and then cases match star. That's nice. I can do repeat cases match star. And now we've solved the whole thing. So that seems to suggest that we could try solve repeat cases match star. And now all of a sudden, we've solved all the goals like this. And then all the goals except this one, and that was very simple. We just do apply, get sum, QED. Yeah, I think you'll trust me that these things, the rest of them, can also be solved as simple. But I'm running a bit short of time, so I'm not going to show you this. So I think, but what this highlights is you have a bunch of nice libraries. You have nice tactics for these. You have automation that's doing slightly more involved things that auto or eauto couldn't solve. And by sort of following this style of doing, of adding these tactics, then it's very easy to sort of tailor your tactics to the proof scripts that you have right now. I mean, if we wanted to, we could say hint extern. So with a cost of 2, you're allowed to do cases match, but only if you're in the lang thing. Then I think that we can just do like that. We don't even have to do this. So whenever you're doing proof search, you're allowed to destruct any match that you find. This thing. And all of this is like the thing I showed you here that actually made the proof script like annoyingly big, whereas here this is pretty nice. This is pretty short. It's very succinct what it does. If you want to, you can say, oh, you're allowed to do this whenever you want. might not want to do that all the time because it might mean that your that proof search takes a lot of time. But it lets you write proofs where you can really focus on what's important, and all the easy things you can just solve automatically. Finally, because I'm recording this from Sweden, in Swedish, when you're in Swedish television and so on, you always have to acknowledge that there are other brands than the product we happen to be talking about here. So TLC is one alternative. That's the one that I have the most experience with. But just so you know that there are other things, there's a separation logic library called Iris that has something called STD++. There's also, I think, included in the Coq Standard Library, a proof language called SS Reflect that uses a completely different style of proving, where rather than putting things in your goal, you have your conclusion is always a list of implications, and then you can do stuff with that. I think this is the tactic that they use to prove I think it's the four-color theorem that they proved using this thing. I might be wrong, so don't quote me on it. But there are a bunch of different alternatives. But I think what's nice about TLC is that it feels a lot like the regular proving that you do in Coq. You don't have to learn completely new things. You just have to learn a bunch of new tactics, but the style is the same, and it gets you a very long way. And that is what's known as the locally nameless representation. So let's talk about representing variables. So typically when we're doing pen and paper proofs and reasoning, we represent variables by using their names. So here we have functions for taking f and x. Here we're taking first and second and so on. So this should look familiar to you. And this is quite like, this is natural for a reason. Like, this is how we've built most of our mathematics. But when we're doing formal reasoning, there are some things that are a bit annoying. One of the things is that names do not mean anything in themselves. They're just placeholders. That means that these terms, for example, they are actually equivalent. This thing takes an x and a y and returns a y. This takes first and second and returns second. Both of them take two arguments and return the second argument. So that means that you get alpha equivalents. So these are the same up to rewriting of names. So that's one thing that's a bit annoying sometimes. The other thing is that the same name can be bound multiple times. So you can have shadowing. So here we have a function that takes an x, it takes a y, and then it uses x as a function, and the argument to that x is another function that also introduces x. But this x is now a different x than the outer x. We have the outer x, which is some x1, and the inner x, which is x2. And this is fine. We can write this thing, we can look at it and not be super confused about what it does, probably. I'm not saying that it does anything useful right now, but we can see that we can follow what it does. But when we do formal reasoning about these things, getting this right is really important. When we're doing pen and paper proofs, we can use what's called the Barendrecht convention. And that's basically just that all variables are distinct, or if they're not distinct, then we can just do sufficient renaming to avoid any problems that we have. This is Henk Barendrecht. He's on the bigger picture here, who wrote the book called The Lambda Calculus, Its Semantics and Applications. I think, is it applications? It's to another mathematician called Thomas Ottman. Unfortunately, we can't do this when working in proof assistance. We can't just say, let's just assume that all the variables are distinct, because we're actually working with programs, as you know by now. So the actual values matter. Things that we have to do is when we're doing substitution, we need to check for shadowing. So here we're doing substitution. If we find a variable that matches the variable that we're substituting, then we replace it by the term that we're substituting for. If it's a different variable, we don't do anything. When we reach another function, if the name of that parameter is the same as the variable we're substituting, then we don't do anything. We leave the thing unchanged. We don't mix up these names. But if the names are different, then we keep substituting under that. This should be standard if you've done a bit of language semantics. And when you're doing beta reduction, when you're writing the dynamic semantics of a function call, then you can use substitution just like this. Replace all occurrences of x by the value b, which is nice. Finally, when we do typing environments, they're just basically association lists. They map variables to types. So variable has some type t if x is bound to t inside the environment gamma. When we have a function call, we can say that let's extend the variable by the parameter and give it by some type t1. And if the body of the lambda can be typed to t2, then the type of the whole thing is t1 to t2. Assuming we have no duplicates in here, that the same variable isn't bound twice, then the order of the environment doesn't matter. We can change stuff around, and that doesn't change the meaning of anything. It's quite nice. Weakening, which is something that occurs a lot in proofs, which is basically saying if you know that a term has some type under some environment gamma 1, then you can extend it by some disjoint environment gamma 2. Their domains are disjoint, and it's going to have the same type. It's not going to change the type of the term. So this is all nice and good. However, we still had these issues, right? That terms that are equivalent don't look the same and things like this. So there is an alternative representation, which is comes from Nicolas de Bruyne. No one outside of the Netherlands knows exactly how to pronounce this. So if there's anyone from the Netherlands listening, I'm sorry, but I'm going to say de Bruyne. And the idea here is that the variables themselves are indexes. They're called de Bruyne indexes. And the index is its distance to its corresponding binder. So here we have the same example as before, but in magenta, I've written the corresponding De Bruyne versions of these. So we have 1 here, because if you see the F here, it passes 1 lambda binder before it finds its binding position. And the X here is 0 because it passes 0 binders to get there. And what's nice about this is that now when you have 2 equivalent terms, they're also syntactically equivalent. These 2 functions are the same, and they also look exactly the same because there are no names. This is a nameless representation. That means that shadowing is no longer an issue. We don't have to worry about, oh, which X is this now? Because because there's a 0 here, we know that it corresponds to the parameter of this function, whereas this 1 corresponds to this thing out here. That's potentially nice. However, things become a bit trickier. So one of the things is that when we're changing terms around, because these indexes are very dependent on their position in the term, we need to be very careful. So for example, when we're doing substitution, so here I'm substituting an index, so that's the n for some term u. Whenever we go under a binder, not only do we have to remember that, oh, we're now substituting, if we used to substitute 0, we're now substituting 1, because now the distance to the corresponding thing has increased. We also have to do something called shifting, which we write with this up arrow, which is saying increase all the indexes of this U by 1. This is because we're now placing it under a lambda thing. If there were any zeros left in this U, then that would refer to this X, and that wouldn't make sense because the U comes from the outside. But we don't want to change all of the things. So instead we have the shifting takes 2 parameters. It's the I, which is the amount of which we shift. And we also have a cap, an upper limit that says only perform shifting if the index that we're looking at is larger or equal to the cap, and that cap increases every time we go under lambda, so that we don't accidentally touch things that were bound inside this term. And now beta reduction becomes a lot trickier. I think I've made my point by just showing you this, but I'll try to talk you through it. So this thing, replace the 0th index by the value v, but shift the value v up by 1 because we're moving it inside a lambda binder. But by the way, unshift the whole term because we've just now removed a lambda binder. You can get this to work, but the formal proofs become a lot trickier. A nice thing about this from an implementation perspective is that our typing environment can now just be a list or a vector or something, where the indexes are just indexes into this thing. So if we wonder what is the type of the index n, then we just look at the nth position of our environment. Similarly, if we type a function, then we just extend our environment by putting the type of the function first in the context. But this also means that the order in the environment very much matters. We can't just change things around, because it's very important that the meaning of the nth index, the type of that, is in the nth position, so we can't change stuff around. Weakening is also tricky because you need to update all of the indices. So if you add a bunch of things to your environment, then you need to shift your whole term by the size of these new things that we added. So we get some nice properties, but our jobs as theoreticians get harder because all the definitions are now a little bit more involved. So there is a middle ground. Here's our friend Arthur Charchereau again. He did not come up with this thing. It's an older concept, but he has a very good introduction paper that I recommend that you read in case you're interested in this, because it's a very nice paper. It's very easy to follow, especially if you've done a little bit of Coq. So the idea is that we use nameless representation for bound variables, and we go back to using named representation for free variables. Okay, so what I mean by this, that means that our lambda terms, they're the same as the de Bruijn indexes, but whenever we sort of peek under a lambda, whenever we go inside a function, we introduce some fresh variable, for example, f in this case, or x, and then we can reason about them using names, meaning we don't have to shift stuff around or anything. So we get the nice property that equivalent lambda terms are syntactically equivalent, but we also get the nice property that variables are names whenever we need to look at them and reason about them. So we can do substitution as before. This is almost the same as before, but it's actually a little bit nicer because we don't have to care about shadowing anymore, right? Because bound variables, they are represented by indices. So if we're saying replace a free variable by some term, then that can't collide with a bound variable anymore because the bound variables are represented by indices. So substitution no longer needs to change anything. There are no special cases for lambdas. It's just everything is really simple. Substituting bound variables, that's also quite nice. And it's nice because, so we call it opening. We write this TM and this little U up here for replace the 0th index by U. And this now is very similar to the substitution for the De Bruijn indexes, except we don't have to shift the U anything. And I'll get to why that is in just a second. We still have to update, whenever we go under a binder, we have to remember that we've gone under a binder so that sort of the indices are updated. But other than that, the substitution function is simpler. Obviously, there's an obvious price that we've paid. There are now two substitution functions. We have substitution of free variables and substitution of bound variables through opening. But both, each individual definition is now simpler. Beta reduction is simple. We just use opening. However, because we have this nice property that substitution is really simple, we can show that opening with a value is the same thing as opening the term with a fresh variable and then replacing that variable by the term, as long as it's a fresh variable, so a variable that doesn't occur anywhere. So I'm just going to read this. Assuming we have a fresh variable, this thing means replace the 0th index with U. This thing means replace the 0th index by the variable x, and then replace x by U. This might look like a more complicated term, but actually substituting a variable, or sort of opening a term with a variable, is simpler because a variable is a very simple term, and substitution is simple because we have the simple substitution thing. The typing environments, they are now back to being maps from variables to types. But a very interesting thing happens, which is here. Because whenever we open a term, we pick the names. It used to be the case that for the named representation, let me jump back, that we had a name in the lambda variable, and we used that, sorry, the lambda term. But now we have the case that we get to pick some x. So intuitively, you can think that we want to pick an x that does not appear in the environment and that does not appear in the term here. But instead, there's a very clever trick called cofinite quantification. Note that this L here doesn't appear anywhere, it just appears out of nowhere. But what we're saying is this type rule holds if there is an L such that any x that is not in that L, this thing holds. And there's a good explanation about why you do it like this in the paper. So I don't have that right. No. The basic idea is that you could imagine saying, oh, for all x that are not in the environment or in the free variables of the term, that's going to be, so that would also work, but that's going to be a bigger hassle to prove because you have to sort of enumerate all the free variables. You could also say that for any, just pick a single one, a single free variable, and use that. That's nice, but then if you have that fact and then you want to do inversion, then what you get out is just that we have something we have a variable that doesn't appear here, whereas with the universal version or with this version, you get a stronger thing out. You get that, oh, it's all the variables that they're not in this set. So I recommend you reading about this in the paper, because it's an interesting balance, sort of. Because we can always pick fresh names like this, the order again doesn't matter. And weakening is straightforward, just as before. We can always extend our environment by things, because we're not shifting indexes around or anything. Final concept here. Because we never reason about bound variables sort of pre-De Bruijn indexes. When we had the nameless representation, we had to sort of look inside, and we could have indices that sort of are not bound in the term that we're looking at right now, because we're sort of looking at a subterm. But here we're always opening terms and replacing them by fresh variables. That means that indices are never out of bounds. A term like lambda1 is meaningless, because which variable are we referring to? And we formalize this by saying that a term can be locally closed. So a free variable x, note this is an x and not an index, that's always locally closed. An application is always locally closed if the parts are locally closed. And for a lambda term, we're saying, again, this cofinite quantification, if there is an L such that for all variables not in L, we can open TM and have it be locally closed, then the lambda is also locally closed. There's an alternative formulation that basically looks at all the indices and checks that there are no out of bounds indices, and you can show that these two formulations give the same thing. But a nice thing about locally closed terms is that we get a bunch of useful facts. So for example, if we have a locally closed term, then opening it doesn't do anything, because there is no index. There's no index that isn't already bound somewhere. If we have a locally closed term u, and we have two different variables, then the order of opening and substitution commute. And if you have a locally closed u, then opening a term with v and then doing substitution. So if you have substitution, distributing over opening. So these are like nice algebraic properties that you can show. And this is also why I said that you didn't have to do any shifting of the u here. That's because the u that we're working with is always going to be locally closed, meaning that there's no worry that there are any indices that are going to start referring to things that it didn't know about before, just because we're moving under lambda. So are there questions about this before we go back to Coq? Because the TLC library has a very nice module for dealing with locally nameless. So I'm just going to walk you through simply type lambda calculus using this thing. Okay, let's jump right in. Let's jump right in. Let's fight Emacs for a second. Yes. So I'm including, among other things, I have libtactics for the tactics. I have libenv for the environment. That's the same that we used before. And I also have libln. That's the library for locally nameless. I'm redefining the auto tactics to use the hint database STLC. We have types, which are arrow types, or just base types. We have terms, which are bound variables, which are indices, they're natural numbers. And we have free variables that are variables. Again, the var type is something abstract that comes from the TLC library. We don't have to care about if it's strings or if it's natural numbers or what it is. It's just an abstract variable type. An abstraction now just takes a type and a term. There's no I mean, this is the yeah, here we have it. That's this thing, right? We don't have a name for the thing bound, but we do have a type because it's simply type lambda calculus. And then we can introduce some notation for this. So we introduce opening, which says replace index k by u. So this is saying now if I equals k, then we do the replacement. Otherwise, we keep the bound variable as is, whereas free variables are left untouched. And when we do have an abstraction, then we need to increase the index. This thing might look broken in two senses. First of all, there's a capital I, and this should be a Boolean, right? But I equals k, that's a prop. But I told you that TLC uses classical logic, and that means that equality is I guess anything really is, you can, because you have the law of excluded middle, you know there's going to be true or not. So the if with a capital I lets you use props here. That doesn't make sense from a computational standpoint, but it makes sense from a reasoning standpoint, because now when you do case analysis on this condition, you get the actual equality back and not the Boolean equivalent that you then have to sort of reflect onto the prop world or lift to the prop world. So that's that. We use this is the open. So we use two things if we want to open with a term, and we just use x if we want to introduce it as a free variable, like that. We have the definition of being locally closed. I just showed you that. The interesting thing here is so a free variable is always locally closed, and the interesting thing is that for the abstraction case, we say that an abstraction is locally closed if for all x not in L, where L is anything that we pick. So we need to show it for some L, we need to show it for all x that are not in this L, that we can open the body of the lambda with this x and show that that is locally closed. It turns out that's not, that seems like a lot of work, but it's actually not a lot of work. And I'm going to add a hint saying that these the constructors is something that we can use. Yeah, we have two kinds of values. We have abstractions or values, but they're only values if they're locally closed. So we don't want the lambda.1. That's not a value. So we need it to be locally closed. This is a function to get all the free variables. Again, notice all the nice syntactic things here: the singleton set, the empty set, the union between two sets. Here we have substitution with some nice notation. Here we have stepping, and stepping just opens the body with the value that we had here. We have multi-step, blah, blah, blah. Context is just an environment of types. And here we have the typing, and the typing, the interesting case is, well, okay, let's look at this. Because whenever we find a free variable, that is well typed with type T, if in the environment gamma, x binds to T. So that's how to read this. So binds, take the variable, a type, and an environment, and ensures that x binds to T in that environment. So that's from the libenv library. We also have OK gamma. That's also from libenv, and OK means that holds if there are no duplicate variables in gamma. So there are two nice things about this. The nice thing is that we don't have to define these ourselves. The other nice thing is that there are a bunch of lemmas and tactics that help us show these things in a very simple way. And then for abstractions, then again, we have the cofinance quantification, picking some L for all x that's not in L. We open the body, so replace the 0th index with this fresh variable x, and then we can extend the gamma with x. Again, this is notation saying gamma and to the end of it, we add x mapping to t1. I mean, ideally, this would be a colon, but colon means other things in Coq already. So here we have some tactics that I've just taken from the library, and the reason is that you need to define this gather vars, and that helps us find fresh variables. So we have a tactic that's called pick fresh, that's going to look at our context, find all the places where there might be variables, and then generate an X that is not in any of these things. Very nice thing. So it basically what it does is, if you have a set of variables, then return that set. If you have a singleton variable, return that singleton set. If you have a context, then return the domain of that context. If you find a term, then get the free variables of that term. But because these things might be dependent on your particular project that you're working on, you have to define this yourself. But then the pick fresh and so on, these are just taken from the library. So is it worth it then? We have this new in-between machinery. So I would say that there might be more things to prove, but everything that you have to prove is typically very simple. So let's prove that if a type is well formed, sorry, if a term is well formed, so it has some type, it's well typed, then it's also locally closed. We'll do that by introducing this thing and doing induction over h type, but we're doing induction star, so that's doing automation after that. So that's that proof gone. If we have a well-typed term, then that environment has to be okay. That has to not contain any new variables. Most cases we can solve automatically. Oh, sorry, I'll make this bigger. But now we have to show that gamma is okay. And basically, we say that for if we have an x that's not in this L that we've gotten by doing induction on has type, then it's okay to extend this thing. We don't have an X, but we have this nice pick fresh tactic. So we can do pick fresh with LX. So this is saying, give me an X that is not in L. And the library just has methods for generating these things. And because it's abstract, we don't have to care about how it works. I think under the hood, variables are just natural numbers. And given a set of natural numbers, you can always generate a natural number that's not in that list, but in some way. So we can generate one that's not in L. And now we can use helper lemma called OK push inv. So basically, this is an OK. It has a push in the end, so it adds something to the end, and we want to invert that, and that's a tactic that exists. Let's just do. If we just write forwards and not the star, then we have these existentials. But it turns out that it's going to be able to find this if we let it using automation, right? You're just going to write a star and then it finds it. We add hints saying that if you have something that's well typed, then we're going to, and what am I doing here? Oh, I think this means if at any point we need to show that gamma is okay, and we have that something's well typed under gamma, then we can apply has type okay. If we need to show that a term is locally closed, and we have that term is well typed, then we can apply has type LC, a different kind of adding hints. So we're already, with just these two lemmas, we're already ready to prove progress. And again, we do induction. This is a special version called inductions, which does generalization of things automatically. So I don't think that one case could be solved automatically. Yeah, we don't have to step through it. The important thing here is that the proof is very simple, right? And whenever I have a star, I'm solving a bunch of things automatically. Here, for the preservation proofs, we need a bit more helper lemmas. This is saying that you can opening with different variables is, I think this is just basically a helper lemma to prove. Let's see what this is used. Yeah, so this is easier to understand. So let's look at that. If you have a term that's locally closed, then opening it does nothing. And now we're in one of these cases where we know that we have this equality that's going to be useful for us, but in order to do that, we need to have an x that's fresh. So we can just say pick fresh x. Now we have an x that's not in anything, and we can use our helper lemma here, and then we're done. Again, we're using rewrites star, doing rewrite and then doing auto things. Substitution and opening is they commute. Here we can introduce substitution. So if x is not in the free variables of t, then opening t with u is the same thing as opening t with x and then doing substitution x to u. Most of this proof is just doing this auto matching. Again, we have these tactics in the library. Cases if says, oh, there's an if statement, to do a destruct on the condition here. So it's just doing a bunch of these things. So I'll just jump. We can do all of it in 320 lines, but the important thing here is that no lemma is particularly tricky. It's very manageable, the whole thing. So once you get into and learn the tactics, then it's very doable. And it's even more doable if you're doing like system F or something that has type variables as well, because then you can, like, again, there are more things that you need to prove. You need to prove that substitution of type variables and substitution of term variables, that they commute and things like this. But each proof is going to be quite simple. I'm going to try to wrap up. I just think that I have a single slide. So what have we been talking about today? We've been talking about tactics and automation, and sort of automation is basically the backbone of any mechanized theorem proving. The point is that that's the thing that makes large proofs feasible, because you don't have to spend a bunch of time on trivial stuff, and it makes your whole proofs more robust to change. So automation, you should really learn how to do automation, at least after you've learned the basics. It makes a big difference to have a good standard library. I think the one in Coq is like the standard library in Coq is fine, but once you've started using TLC, then you don't want to go back, because there are so often where you sort of where you have to prove boring things about lists, for example. And with a good library, you can just have a tactic that says, oh, by the way, here's a boring thing about list. Please solve that for me. And TLC lets you do that. Name binding and substitution is one of the things, like, we don't really care about it when we're thinking about a programming language, but it's one of the central things in programming language theory, even though it's boring and technical. And having this locally nameless thing is one way of keeping definitions simpler. And again, having good library support helps a lot here as well. And so with a few minutes over time, sorry about that, I think we're done for today. So thanks for listening.
Great. Thanks a lot, Elias, for that. And then see you all in the next couple of weeks. We will have the next lecture will be a guest lecture by Magnus Marin, where he will talk about Hull and Hull 4. So I hope you will come to that. So thank you for today.
Thanks.